Hello friends, today we will discuss the new concept series which is thermodynamic concept for engineering design. So this is the first video of this series. So here we will discuss and to know the column operating pressure calculation. So first of all you should know that the column, which is the widely used equipment or unit operation in oil and gas, chemical, petrochemical industry where we do the separation. So this is about me. I'm a presenter, Lokesh Kumar Singh, CUMD Petro Horizon Oil and Gas Engineering Private Limited, and this is about my qualification, education, and my experience. So to know more about me and my company, you can visit our company website petrohorizon.com. So what is fractional distillation column is widely used unit operation in refinery, petrochemical, chemical, and oil and gas industry. So whenever separation is required, we use fractional distillation column. In refinery, you might be knowing that there is ADU, VDU unit. So AD is atmospheric distillation unit and VDU is vacuum distillation unit. Atmospheric distillation unit means operating pressure of the column is atmospheric pressure, and vacuum distillation unit is the operating pressure of the unit is below atmospheric pressure. And we also have the other type of column, fractional distillation column, like demethanizer, deethanizer, depropanizer, and debutanizer, etc. So for design engineer, whether uh, in any industry, so first task is to fix the operating and design pressure of column based on the feed composition, temperature, and pressure. To start the designing of fractionation distillation column or simulation on Aspen HYSYS or any other simulation software. So design engineer try to keep operating pressure minimum so that the design pressure is also minimum. Therefore, the initial capital cost of column installation is minimum. That means if we have the minimum operating pressure, so our design pressure will also be minimum, and the thickness calculation for the column walls will be minimum, and so that means the initial capital cost for column installation will be minimum. So design engineer select the operating pressure of column so that the vapor phase fraction of the covering component is maximum. That means the top head product. So in this lecture, I will teach you to calculate and select operating pressure of column for maximum separation efficiency of column. For simulating column on Aspen HYSYS, we should know the operating pressure and temperature of column apart from feed flow and feed composition. Therefore, it is mandatory to calculate and select the column operating pressure before starting simulating column on Aspen HYSYS. So here comes to the main topic, which is the column operating pressure. So this is our column. I have just depicted it like this. So this is feed, and at pressure T, temperature T, at pressure P, sorry, and temperature T, and this is the n number of moles of feed, and this is the condenser, this is the cooler. So from here we collect the overhead product and we recycle some of the product to improve the quality or the purity of the overhead product. Similarly, here in bottom we have a reboiler here. So partially we collect the bottom product, which is heavier product, and this is lighter product. And from the top head is lighter product and this is heavier product. So and the partially we will vaporize it again and we send it to column for further separation. So the first thing we design a column, when we design a column, is to calculate the operating pressure and design pressure based on the feed. So in feed, what we have, the feed composition, feed temperature, reboiler, and then we need to see the reboiler heating duty and condenser cooling duty. So basically it's a vapor liquid equilibrium calculation concept, because when the vapor is coming here and this boiling point feed, which is partially liquid and partially vapor, is coming here, they are in contact with each other, and every stage it has number of plates. So they are in equilibrium, the vapor liquid come in equilibrium and then they pass to other stages. So that's the reason that it's a vapor liquid equilibrium calculation concept. It is explained by the Raoult's law. So here there are two major assumptions required to reduce the vapor liquid equilibrium calculation to Raoult's law. First is the vapor phase is an ideal gas. It means Raoult's law can apply only for moderate to low pressure because gases or vapor behave ideally at moderate to low pressure. That's why we try to keep um, operating pressure of the distillation column like ADU, VDU, either atmospheric pressure or below atmospheric pressure, so that our Raoult's law applicability is valid. So the second assumption is the liquid phase is an ideal solution. It implies that it can have approximate validity only when the species that are comprise the system are chemically similar and Raoult's law are valid. So what that means, that chemically similar, like toluene and xylene and paraxylene, these are chemically similar species. So if we mix together to these component and we make a mixture, it is like an ideal solution. So what is the mathematical expression which reflects these two assumptions? So this is YIP equal to XI and PI set. This is Raoult's law actually. So YI is the vapor phase fraction of the component I and XI is the liquid phase fraction of the I, component I, and this P is the total pressure of the column or operating pressure of the column, you can say, and this PI set is the vapor pressure of the pure component I at the temperature of the system. So this I could be anything, like for binary system I is 1 to 2, and for if the component is more than 2, so I can be from 1 to n. So this is like further I have write it YIP equal to XI PI set. So YIP is gives the partial pressure of component I. So let's say example, if we have a mixture of alcohol and water, then it is a binary system because there are two component only. Here we can assume that alcohol is a component first and water is a component 2. So if we feed this mixture into a column at saturation temperature, that means at bubble point of water at some pressure P, which is more than the column operating pressure. The pressure which is feeding into the feed stream pressure should be higher than the operating pressure of the column. Otherwise, in simulation, your model will not converge because it cannot enter into the column. So the mixture will flash inside the column and it will form two phase. When the higher pressure, which is the pressure higher than the column operating pressure, the stream will enter into this and there will be a pressure drop, so it will do the flashing. And the region of flashing is another region of flashing is that it is this feed stream is at bubble point, so it will easily flash. So therefore, as per the phase rule for non-reacting system, we know that F equal to C minus P plus 2, where C, this is C is the number of component. So here number of component is 2, water and alcohol. P is the number of phase. So when it is getting flashed into the column, so number of phase is 2, liquid phase and vapor phase, and F is the degree of freedom. It tells us how many state functions are required to define the column. So here we have two component and two phases, so our degree of freedom is 2. That means minimum 2 state function is required to define the operating column. So that means we need both P and T to define this system. We already know the feed temperature, TS, operating pressure we need. That's why we need to calculate the operating pressure of column. So you might be understanding that what I mean to say, that by degree of freedom we could know that when our uh, column in the simulation will converge, or when the feasibility of calculation is possible if we know these minimum parameters to define the system. So this is now I will tell you how the Raoult's law gives us the concept of calculating the operating pressure of column. So this is YIP equal to SI PI sat. So YI equal to XI PI sat upon P. So here P is the operating pressure of the column and Y is the fraction of component I which we want to recover in vapor phase. That means this is overhead product which we want to collect or which we want to separate from the mixture. So this relationships of equilibrium state so that Yi is inversely proportional to column operating pressure. That means if the column operating pressure is more, so the Yi, which is the top head product, the vapor fraction of top head product is less. That means the vapor in the top head product we are getting less purity and we are getting less product which we want to separate. So if the pressure is low, that means Yi is less. That means the product quality here is improved if the pressure is low, and the Y component and the vapor fraction of component I in top head product increases. That means the second component is reduced and the Y is increased. So that means the low pressure of column operation is favorable for getting the high purity of the recoverable product. If so, what we can do to find the optimum pressure? So we will make a table on various pressure and we'll check the value of y1. So here, so take some trial value of P. For this we will calculate X and Yi. So this is P. Let's say I start from the atmospheric pressure 100 kilopascal, then 90 kilopascal, 80 kilopascal, 70 kilopascal, 60 and 50 and so on, and we will calculate the Xi. No, we will calculate Yi. Xi value will take ourselves from 0 to 1 with some interval. So how to calculate Yi? So this is the formula to calculate Yi. Xi Pi sat upon P. This is from the Raoult's law. See, this Raoult's law is equation is valid at equilibrium state, right? So from this equation we can calculate the Yi. So for calculating Yi we need P, Xi and Pi set. So Xi we have already chosen ourselves from 0 to 1 and P we have taken the trial pressure. So from here we can take the value and then Pi set we can calculate from the Antonio equation which is ln Pi set equal to A minus B upon C minus T. So this is at given feed temperature. This is given feed temperature. So here the P is in kilopascal and T is in Kelvin. So when you put these values like A, B, C for that pure component, because this A, B, C are Antonio constant and these values are available in standard books or like a data book like Perry and other books. So for each and every pure component you can find A, B, C from those, and then you know the component there is alcohol and water. So for alcohol you can find A, B, C, and which we want, which is our first component which we want to separate. So if you will take the A, B, C value here for alcohol to, and then similarly you can take for water also to know the saturation pressure. So now you know the Pi set also, so you can calculate the Yi and then you can list here. So for alcohol water mixture, if you want to recover alcohol, so then at a given feed temperature we will calculate the P1 set from Antonio equation like P1. So we can take it P1, so A minus B upon C minus T. So for alcohol A, B, C value we will take from the pure properties given in data book or constant value. This is Antonio constant value, so we can take from the data book like Perry. So after that we'll assume that some trial value of the column pressure P and calculate the Yi from value X value from 0 to 1 with some initial interval like I shown you previously, that we will take some one value here, then based on that one value and this x1 value from 0 to 1 will calculate y1. Similarly we will take another trial pressure value and we will calculate the y1 based on x1, and similarly we will go on keeping trial the pressure P1 till the y1 is 1. So here, then after that we can plot this pressure here and then x1 y1 here. So we will get a curve like this. This is p x1 y1 curve. So this p x1 y1 curve, and this is px1 curve, and this is py1 curve. See how you will plot this curve. See, you first take this value, one value from here, corresponding value x. So first plot px1. So from this value take this 0 1. So here you can take, then from this value you take this point 2. So similarly you can plot this pressure, this px1 and py1. So here if you see, this px1 is a saturated liquid line and this is the saturated vapor line. On top of this liquid saturated line, this is subcooled liquid region, and below this saturated vapor line, this is superheated vapor region, and between these two lines, this region is two phase region in equilibrium. So this point, so if we take a x1 fraction of 0.6, so that means, and we want to know the corresponding bubble point and dew point. So at this point, this gives the value here, the bubble point pressure, and this gives the dew point pressure at this given temperature. So let's say at bubble point our x1 is 0.6. We want to know at bubble point what will be our y, this y component. So we can draw like this. So from here we can know the y component. Similarly for dew point we know the liquid composition. So if we draw here, and correspondingly we can check the because this point is on liquid line, so it will give liquid fraction. This point is on vapor line, so this will give vapor fraction. So similarly you can read x1 and y1, because if you are reading something from this line, so you will read y1 here in the same fraction, and if you are reading something from this line, so you will read x1 from this one, because both x1 y1 is plotted on this x line, horizontal line. So in this video we have explained you how to calculate the column operating pressure, because see here, once you find the trial values for pressure P1, P2, P3, you need to check that value of pressure where the Y1 fraction will come the maximum. So that will be our operating pressure. So and I will also told you the Raoult's law for ideal solution, so which is YIP equal to XI and PI set, and how to plot P x1 y1 curves to know the dew point and bubble point pressure and composition. So in the next video, or the new video, I will teach you how to optimize the column operating temperature while operating and design pressure of column is given, and how to plot Tx1 y1 curves to know the dew point and bubble point temperature. And so thanks for watching. This is Petro Horizon offering for petroleum, chemical and mechanical engineering students. We provide 1 month duration value-added training courses for first year, second year, third year and final year students. They can enhance their technical knowledge, as well as they can learn the design skills in this short course, which is of 10,000 to 15,000, depend on the course they choose to do. And we provide second course, which is 6 month engineering design skill development training and placement assistant course, and here we provide 300-hour rigorous training and certification, and at the end of 6 months we give them opportunity to work in a renowned MNCs and domestic and international design organization. Our training fees is 50,000, which can be paid in installments, and this is for third year and final year students only. For chemical, petroleum, mechanical engineering students, this is to be noted that See, third year and final students also do project in third year and final year. So we provide free consultation to third year and final year students for selecting the project work in design field, which will give the high gravity in their curriculum if you do the design project, because normally the people do the cut paste and copy paste from the here and there, but if you come to us, you are interested to do some design projects, so we'll help you and we'll guide you how to do that and how to perform extraordinary in your curriculum. So this is here there is another offering. We are providing 3 days demo training and awareness class at their own company office to know exactly what is engineering design and job prospect, because most of the students, they don't know what is engineering design work actually. When somebody heard about the design, they think that this is AutoCAD or CATIA or something similar software, which is not the work of a BTech engineering student. This CAD work and this other software which are used for drafting purpose. So this is only for the diploma students. So this engineering design skill is entirely different. They don't deal with the AutoCAD. So we have many other concept and software which you need to know. If you will come to know when you will join our 3-day demo training classes, which is absolutely free for everyone. Because if you want to know that what is engineering design, at least you need to attend 2 to 3 days demo training classes, then we can only teach you and make you understand what is engineering design and what is the job prospects and how it is highly paid job in the market. So right now we are successfully running 2 training batches since May 2017. One is value-added training batch which is of 1 month duration. So here we have teach the student the foundation course for S1 HASS simulations. So, and the second is mechanical design engineering batch, which is of 6 month duration. Every batch we keep maximum 10 students to make, because if the student is more, we will not be able to make the crystal clear concept of each and every one, because we need to give them the full attention. That's why our batch size is very small as compared to if you see the other institution which give training. So this is our company office address: Premnagar, Nandagi Chowki, near Punjab National Bank, Suddowala Road, Dehradun, Uttarakhand. So you can contact us on petrohorizonindia@gmail.com and info@petrohorizon.com, and these are the number mentioned, so you can call us on these numbers to know anything. Please subscribe our YouTube channel to get updated with new videos. You can also visit our company website, which is petrohorizon.com. So there you will find a direct link to YouTube video where you can watch our channel all videos at one place. So thanks a lot once again.